I have in my notes another problem set, although that would be for 2 weeks from today. Why don't I just give you that as well, so as long as we're doing it. Monday from next Monday. Okay, so let's look again at our electrocapillary equation. And what we see is we have the surface tension, derivative of the surface tension versus the electrode potential. Now, so if we consider all these parts in turn, what we can get first of all is an equation or an electrocapillary curve, which is the surface tension versus potential. And how do we get that? We can measure the drop time, the time of the maximum drop time. And if you remember, that drop time maximum is directly related to the surface tension, so we can get the surface tension directly from those measurements. And if we plot surface tension versus potential, we get this parabolic change curve, and we get a lambda max value right at the top. If we look at our equation, though, we can plot the surface tension derivative versus over the potential, d lambda d E, and we can then take this curve and do that derivative, and that will give us the surface excess of our particular species that we're interested in. And depending on the shape of the parabola, we get maybe a curve that looks something like that. And then if we take this derivative of the surface excess on the metal and take the derivative again, we get the capacitance versus E. And I'm drawing it as not a straight line, but with a sort of a subtle dip in the middle. And those relationships work out because it turns out that d lambda is equal to minus, so holding everything else constant, and then the charge on the metal versus the thing happens to be equal to the capacitance. Okay, holding again everything constant. So by measuring the curve here, we can do the derivative of that and get this curve, and then doing the derivative again, we get the capacitance as a function of potential. Now it turns out we can actually measure the capacitance directly, so we can also go from the reverse back to here to get the surface tension. So if we look at the capacitance, we can get the excess charge on the metal, and then we can get the surface tension. So we can either do it with the normal dropping mercury electrode and get the capacitance, or we can measure the capacitance in another way and go back to get the surface tension. Turns out that the capacitance at mercury is on the range of 20 to 40 microfarads per square centimeter. So a fairly large capacitance. We often then, using these curves, we often also want to know things like what's the relative surface excess amount of potassium ion. In other words, what's amount of potassium ions in excess at the electrode surface. Well, what we can do is we can take the derivative of the surface tension versus the derivative of the free energy of potassium chloride, holding the potential and the chemical potential of the modifier constant. We can get the And knowing the fact that chemical potential of the potassium chloride is equal to the standard chemical potential of potassium chloride plus the change in the activity of potassium chloride, we get this sort of relationship. By looking at the change in surface tension with change in activity of KCl, we can get the idea of the surface tension, the surface excess amount of potassium ion. And so what we can do is we can derive, knowing the electrocapillary curves, and by changing the activities, we can actually derive the values for the excesses. And so we can get curves like this. Where the initial curve might be surface excess on the metal. But we can also look and see what is the surface excess on the for the positively charged species, or the surface excess for the negatively charged species. Okay. And so this would be the net charge on the electrode, but then we can break that down into the ionic components of that surface excess. And so in this case, sigma plus is just going to be equal to ZF, the amount specifically absorbed of that species, and so it might be potassium ions, and sigma minus would be equal to ZF, specifically absorbed amounts of the anion, chloride, and so on. Notice in this curve, which is actually basically with a curve you'd see for sodium chloride or potassium chloride, some interesting things. One is that at the PZC, this would be E, and we've got below the PZC on this side of the thing, we're going in a negative direction. Below the PZC, we've got a positively charged electrode. So at a positively charged electrode, we expect a couple things to be true. One is, since it's positively charged, we expect anions to be attracted to the electrode and be absorbed to it. And in fact, that's what happens. You notice here that the excess amount of chloride ions is attracted to the electrode, and so the more positive we go, the more excess chloride we get. And the opposite is true. As we go to a more negative electrode, we expect the positively charged species to be attracted to it. In fact, you see that's happening. The potassium ion or sodium ion would be attracted to the electrode surface, and as we go increasingly negative, we see more of it. What should be interesting to you also, though, is that not only at positive potentials do we see an excess amount of potassium or sodium ions, but at positive potentials we see an excess amount. And why is that? Well, it turns out that chloride is so strongly absorbed at this particular electrode, the mercury electrode, that there has to be some additional amount of specifically absorbed potassium ions and sodium ions to counterbalance the charge on the chloride ions. Turns out that because of the affinity of the chloride for mercury, chloride ends up being specifically absorbed. In other words, it's a naked anion stuck right to the mercury electrode, and the potassium ion undergoes a much weaker sort of absorption, non-specific absorption. So there's quite a strong attraction for the chloride ions to the mercury, and they stay stuck to the mercury. And in order to compensate for that, the potassium ion has to be dragged along and be also absorbed at the same time. So for a very simple looking experiment where we just measure drop times, we actually get quite a lot of information. We get a very interesting set of information about the interfacial structure of the mercury electrode. Stuff that, for example, when it was first developed in the 30s and 40s, you could not get any other way. And so that's one of the powerful things people were able to do. Now the question people then